So the next section of notes is dealing with two things that we have now talked about. We've talked about this concept of potential or electric potential or EMF. We did that in the last section, and we talked about current. We did that in the first two sections. So we're going to talk in section 22.4 about how these concepts are related to one another. So a battery, we know it's an electromotive force, but it's a source of potential difference. It gives us that positive and negative terminal, and it gives us what we call potential difference. So we'll talk more about that. The current that flows through the wire that's connected to the battery is a consequence of this potential difference. So because the ends of the wire, so if I were to draw a little battery up here, right, I got my positive side and my positive side on top, my negative side on the bottom, and then there's just a little wire that that connects the two together. Well, the wire is connected to the terminals of the batteries, and there's a potential difference between the two ends, and that potential difference is equal to the potential difference of the battery. So this battery, a regular battery, is 1.5 volts. So at the bottom, I have 0 volts. At the top, I have 1.5 volts because that's the strength of the battery. So then, as the current flows through the battery, right, it has to have a voltage drop of 1.5 volts because it's going from an electric potential of 1.5 to an electric potential of 0. The potential difference causes a current to flow in the direction of decreasing potential. So it goes from 1.5 to 0. So if you don't ever really connect car batteries like this video is on the right, don't ever do that. But if we have a power source, there are many things that we use that are pretty similar to just a wire. So up top, this is a very common appliance. It's called a toaster. A toaster has wires pretty much that just run across it, and that electric potential is dissipated on the wires, and the wires are caused then to heat up, and that heat is so large that it's able to cook our bread that we put into the toaster, right? On the bottom, we have a light bulb. A light bulb is the same concept. It's got a tungsten filament that goes across it. The wires, it's just one simple wire, one simple tungsten filament. The electricity of 120 volts goes across it, causes that to glow and to heat up, and then there's gas inside the light bulb chamber that allows it to further glow. And when a light bulb breaks, that little tungsten filament on the inside kind of snaps, and then the light bulb doesn't work anymore. It creates a short circuit, which we'll talk more about later as well. So, two factors that determine how or what the current is. And remember, current it's our charge flow in our given amount of time. So there are two factors that determine what that current is. And one is the potential difference, so the voltage of the battery, and the other are going to be the physical properties of the wire. And this is assuming we have the world's simplest circuit, which is just a wire going from positive to negative. Obviously, we're going to get way more in depth, and we're going to put light bulbs and stuff in the circuit. We're not going to get too in depth, but we'll get a little in depth. But we do know that the greater this potential difference is, so the greater the voltage of the battery is, the greater the current is. So the current is proportional to the potential difference. So if I have a 1.5 volt battery versus a 9 volt battery, it's going to have more current because it's got a greater electromotive force. So I can play around with that by adding multiple batteries. So if I have one battery versus two batteries, I will have more current. So adding a second battery increases the current. And this should make sense, right? More and more voltage is going to be more and more powerful, right? We need 120 volts in our house to run stuff. We only need 3 volts in our remote to make our remote control work. The other thing I can do is kind of play around with the resistance. And this is something that's popped up on the AP exam before, but this concept of messing around with the wire dimensions. So if I increase the length of the wire, it'll decrease the current. I can increase the thickness of the wire and increase the current. There's a couple different things that I can do to manipulate that resistance. And this concept known as resistivity. And resistivity is a physical property of the wire. So like I said, it has popped up on the AP exam before. There's a question about Play-Doh and the thickness of Play-Doh and the length of Play-Doh, because Play-Doh is a conducting material, so we can actually play around with it in circuitry. So it's a concept that we do talk about, and we also do a lab. It's called the resistance in a wire, where we look at a couple different gauges of wire and length of wire and see the internal resistance of that wire. But we can also have different types of wire. So on the left we have copper, on the right we have iron, and different materials have different currents because of, again, this concept of resistivity and the physical material that makes it up. So in your house, a lot of times you have copper wire. Now, what's the problem with copper wire? Well, it's kind of expensive. So sometimes in your house, especially if you have a thick wire, so if you upgrade your house to 200 amp instead of 100 amp, you will have a much thicker wire. So in order to save some money and to not make those out of copper, they make them out of aluminum. Well, aluminum has other issues. It oxidizes, so electricians take special precautions to make sure it doesn't. And then in your headphones, a lot of times some of the headphone companies will advertise that they have gold in the headphones, and the gold is a really good conductor, but it's really expensive, but it's supposed to be really high quality. So there are different types of material, and that will have different effects on the current as well. So resistance is a measure of how hard it is to push charges through a wire. So resistance, you think about resisting something, how hard you have to resist. A large resistance implies that it's hard to move charges. So if I'm looking at my current is delta Q over delta T, the greater that resistance is, the less the current will be. So the current depends on the resistance of the wire and the potential difference across the wire. Because remember, the stronger that my potential difference is, the more my current will be, the more charge it'll be able to push in a given amount of time. So with that, we get a formula, and that's that the current is equal to the voltage in the wire divided by the resistance. Now, if anyone has ever studied resistance or circuits before, this should jump out of you. And we're going to talk more about this later, but this is known as Ohm's law. Ohm's law governs the relationship between voltage, current, and resistance. But for right now, all we care about is that the current through the wire is equal to the voltage drop across the wire divided by the resistance of the wire. So let's take a closer look at what the resistance of the wire is. So the wire's resistance is the voltage divided by the current, and the unit for resistance of the wire is measured in ohms. 1 ohm is 1 volt per amp, and we do use the Greek letter capital omega to talk about ohms. Again, if you've ever done circuitry before, you've seen this and you're familiar with this. But resistance makes up a couple factors. So resistivity is one of the factors. In resistivity, we use the lowercase letter rho and characterizes the electrical properties of the materials. So copper versus iron versus tungsten versus, there's so many different, what the material's made up changes how much resistance the wire has. Materials that are good conductors have low resistivity. Why is this? Well, the more resistivity that the wire has, the more voltage gets dropped on the wire than it does on the actual components that you're trying to power. So coming from from We Energies, from the power plant, there's a much larger voltage. But as it travels across the wires to get to your house, it actually loses some of that voltage because of the resistivity of the wire. So we want good wires from the power plant to our house, because that will make sure that we lose the least amount of electricity, otherwise known as voltage drop, across that wire. So the different types of materials have different resistivities. But also interesting to notice is that the hotter something gets, the less resistive it is. And that'll have another effect on especially light bulbs, right? So light bulbs, when they're when they are cooler, they have more resistivity. And I don't know about you, but I've seen light bulbs when they burn out, it's right when you turn them on. And that's because they wear down over time and they have that increased resistivity, almost 10 times the increased resistivity when they're cold versus when they're hot. So not that your light bulbs are burning at 1500 degrees Celsius, but they do their resistivity decreases as they warm up. Now, another interesting thing is resistivity of muscle versus fat. Almost twice as much resistivity of fat. So a lot of scales have this calculator in it where you can stand on it and it measures and predicts your body fat. And the way that it does that is you can't have socks on. You have to be barefoot when you step on those types of scales. But it sends electrical impulses through your body and it measures the resistivity. And it knows that this high resistivity is fat and this low resistivity is muscle. And it says, well, you're somewhere in between because nobody is 100% fat. But it can determine your percentage body fat by this concept of resistivity. So it's kind of a cool little concept. So we do get then a formula for calculating the resistivity or the resistance in a wire, otherwise known as. So a wire that's made up of some material has resistivity rho. The length and the cross-sectional area are what matters. So this formula, like I said, it has popped up on the AP exam, and I mentioned that Plato activity. And we'll do the resistance in a wire activity and hopefully kind of see that a little bit. But I have a great analogy for this. You're walking down the hallway, right? And think of the resistance in the hallway as the other students that are in the hallway. Now, the more students there are, that's kind of your resistivity thing, right? So more and more students, that's like copper versus gold. It's different amounts of resistivity, and that's a physical property of the hallway. So if you think about how long it takes you to get from one end of the hallway to the other end of the hallway, the longer that hallway is, the more time it takes you, the greater that resistance. But if I have 100 people in the hallway, right, and the wider my hallway is, the easier it is for me to make it down that hallway. So resistance of a wire is determined by not only the length of it, but also its cross-sectional area. The fatter that wire is, the less resistance that is. And that's why when you have wires that take higher current, you have to have fatter wires. So if you look at like the wires in your headphones, right, they're very, very, very small. But if you look at the wires that are actually bringing power to your house, they're very, very, very thick. So a couple different examples there. So this formula is needed for lab 7.8, which is the resistance of a wire lab. And we'll be able to see that a little bit better. So with that, we're pretty far through chapter 21. And we're going to take a break and we're going to look at a couple labs. And the two labs we're going to look at are going to be taking a look at what happens when we hook batteries up in series and parallel. And then we're going to be going ahead and taking a look at that concept of resistance in a wire. But we also need to take a look at back then and say, okay, we understand this concept of resistance and we understand this concept of current and how it's based on resistance, right? So we're going to need to get a formula, and we already looked at that a little bit today, but a formula that links these two together, and that'll bring us into Ohm's law. So that'll be the next section of notes, but we'll be taking a closer look at batteries in the next segment.